Hello, good afternoon, Cynthia, Zaina, and Arita. Let me ask first, what major are you taking?
Math and Science. I'm TPA. VIT.
Okay, so we have one math and science, one TPA, and one VIT student. Perfect! Alright. So, this is my basic engineering project. Okay? So, we were tasked to design a frame. This is mine. Frame of a building that could withstand earthquakes. Alright? And there was a maximum amount of sticks that we could use, which is 100 sticks. And I think, if I'm not mistaken, I used only 85 sticks in my building. So, this is my face, so that it is proof that I am doing the presentation. And this is my earthquake-resistant building design. So what we have here are 3 floors. It's called the Crooked Church. It looks like kind of like a church, but it's crooked, right? And it has X's as the connections for the walls. So there aren't any walls, but since it's the frame, there needs to be a support for the walls. So this is the X's on the 3rd highest floor. And in the 2nd floor, we have not X's, but we have beams. And this is the beams. And then finally, the most strongest support would be, the most strongest frame would be in the 1st floor. We have around 5 beams in the 1st floor. And we have a weight, extra weight in the middle so that it could withstand earthquake and essentially just provide more strength to the building. Okay, so my project focus question is, how can we make a earthquake resistant building? Well, this is the way, and we would want to test it, right, to show that this is earthquake resistant building. But what we have here is our collaborative busing project. Here it is. All right. So Mr. Agam taught me that the project could be put up here, and then there's gonna be a machine that can make an earthquake happen. But the machine is not yet done. Why? Due to time constraints. So how the machine works is this will move because of this. There's a contraction here that lets this to spin, right? And when it's spinning, this one's also spin, the small blue one also spin, hence causing an earthquake by the wooden plate. So yes, this is not done yet, but when it is done, the earthquake will happen here, and our project will be put here to test whether it's earthquake resistant or not. So in conclusion is, yes, I believe, my hypothesis is this will not break, and since this is the best product ever, this will not break, and it will withstand the earthquake. And my mission in this video, in this presentation, would be how can we make an earthquake resistant building, especially we're living in a ring of fire. Indonesia's living in a ring of fire, and I took one of the problems of the Aceh tsunami, which was caused by an earthquake, and there was a lot of buildings that was torn apart because they weren't earthquake resistant. Hence why I made this. But this is also in line with the big question, because why should visionary leaders adapt, right? Why? Do you know why? Okay. Well, how do visionary leaders adapt is we need to figure out future problems and solve them right here, right now, so to prevent those problems, right? And in this earthquake resistant building, we can prevent those, because let's say there's an earthquake. Oh, I don't have to go anywhere. My house is earthquake resistant. Why should I go somewhere, right? It's already earthquake resistant. That's being a visionary leader. And the relation with the learning outcomes is that complex thinking needs to be earthquake resistant, as well as critical thinking. To make this design, you need to be critical, and you need to have a complex mindset. And expert thinking. Don't forget expert thinking. That's the most important one. I believe this is done, a show of my product of basic engineering. And with that being said, I thank you, and thank you. Oh,